be defined as the turning effect of a force, turning effect produced by a force. Its formula is given as the force times perpendicular distance and hence its unit is in Newton meters. So what do we mean by force times perpendicular distance? It just means that moment of a force is the product of a force and its perpendicular distance only. That is, the force and the distance from the turning point has to be perpendicular. So let's say we have a 20 Newton force here, and the distance between that force and the turning point is 3 cm, for example, 30 cm, for example. Then the moment can be calculated as follows: force times perpendicular distance, 20 Newton times, this is in cm, so you have to convert it to meters, to 30 divided by 100 is equals to 0.3 meters, so times 0.3, and this is going to give us 6 Newton meters. Alright, so the reason why we're even buttressing on the force being perpendicular to the distance from the turning point is because we can have cases like this where, for example, let's say this is distance from a turning point, and then you have a force which is acting at an angle, so either the vertical or the horizontal. So let's say this force is acting at an angle of 30 degrees to this distance x. So let's just call the distance x, and let's call the force F. You are asked to calculate the moment of this force about this turning point. How do you go about it? Well, first of all, this force you see here is not perpendicular to the distance. So we have to resolve the force to its horizontal and its vertical components. So its horizontal component is going to be what? F cos theta. So its vertical component is going to be what? F sine theta. And thus, the moment of this force is going to be given by F sine theta times distance x. Now, many students make this mistake. Let's say this angle was not inclined at 30 degrees to the horizontal. Let's say instead the force was inclined at 30 degrees to the vertical. Do you still resolve this as F sine theta and this as F cos theta? No, it will be the reverse. This time, the vertical will be F cos theta, and then the horizontal will be F sine theta. Now, an easy way to remember this is wherever the force or a vector is inclined to, we take it conventionally as resolving to the horizontal. So we always use F cos theta whenever the vector is inclined to that axis. And whenever there is no inclination, we use F sine theta. So just remember that. Okay, so I want you guys to understand the principle of moments. What is moment actually? What is its application? And how can we solve questions under this topic? So this is a turning point, and this is a beam, e.g. a ruler or meter rule or even a straight plank. If we balance this plank on or at the center, it is said to be at what? Equilibrium. It is at equilibrium because the distance from the fulcrum or the distance from the turning point are equal on both sides. And assuming this beam is uniformly massed, that is, there's no side heavier than the other, this beam will balance horizontally without tilting to any side. Now, let's say we add a weight here, a weight or a force here. Immediately, this is going to turn to this direction and might even fall over. So the moment for this weight on this turning point is given by what? The weight times the distance from the weight to the fulcrum. So let's just call this distance x. The moment here is going to be what? Wx. To balance this, we have to put another weight of equal mass here. And not just that, the distance has to be what? The same. X. So the moment intended to turn the beam in this direction is also Wx. What I'm trying to show you here is that equilibrium can only be attained when the clockwise moment is equals to the anti-clockwise moment. So this is the clockwise moment because going in towards the right direction, and this is what anti-clockwise moment, which is going towards the left direction, turning towards the left. So that's the first principle of moments. Clockwise moment has to equal what? Anti-clockwise moment for equilibrium to be attained. Now, let's say for example, we increase the weight. Let's say we put a bigger mass here. What do you think will happen? There will be no equilibrium and this beam balance will fall towards this side. Why? Because this weight is heavier and they are at equal distance from the fulcrum. Now, how do you think we can balance this heavier weight? Let's say it is 3 times heavier than the weight on this side. How do you think we can balance it? Well, it's very easy. We move the heavier weight closer to the fulcrum. So we are going to move this weight to a point where the distance is just 1/3 the normal distance. So by the time we take the the anti-clockwise moment, we're going to have what? 3w times 1/3x, and obviously you see that 3 cancels out, so we're going to be left with wx. We're back in what? Equilibrium. So the way we balance this beam is by what? Changing the distance between the weight and the fulcrum, or changing the mass of the weight. If the weight is too heavy, we move it closer to the fulcrum in order to try to balance it with the other side. If it is too light, we move it away from the fulcrum so it can have more what? More turning effect, more leverage. So there are two ways we balance. Either we increase the distance from the turning point, or we decrease or increase the weight. And those are the two quantities that make up the moment of a force. In physics, what we actually use is a meter rule, which is usually 100 cm long. So let's assume that's a meter rule I've drawn. This meter rule is 100 cm, 100 cm long. 100 cm is same as saying 1 meter. So in your question, you see a term like uniform meter rule. What this means is that the mass of the meter rule is even across its length, so it can balance on the 50 cm mark. That is half of the distance. And then if you see the term light meter rule, it means the meter rule is massless. The meter rule has no weight. So we can ignore the weight of the meter rule. That's what that means. So now that we know that the meter rule is 100 cm long, I want to make some calibrations. So this is going to be the 0 mark end, and this is going to be the 100 mark end. So a uniform meter rule will balance horizontally at a point that is half the distance, which is 50. Half of 100 is 50. So at a point 50 cm, we can balance a meter rule horizontally, and it will stay without tipping to either sides. Okay, so the distance from here to here, from the fulcrum to this end, is 50 cm. The distance from the fulcrum to this end is also 50 cm. I just want you to note that. Now you can have a question like this. The question can be, if we place a weight, let's say for example of 20 Newton at the 20 cm mark, what weight are we going to place, or rather, where are we going to place a 50 Newton mass on the other side? So where are we going to place a 50 Newton mass on the other side? 50 Newton is heavier than 20 Newton, obviously. So how do we balance a heavier weight on the right hand side? Because 50 Newton is heavier, it has to be closer to the fulcrum. If this is the 20 cm mark, it means the distance between the 20 Newton weight and the fulcrum is 30 cm. So the 50 Newton weight has to be placed somewhere less than 30 cm from the fulcrum, and we're about to find out where. So I'm just going to draw the weights. 50 Newton, and we are to determine the distance which we place it from the fulcrum. So from our principle of moment, anti-clockwise moment is equals to clockwise moment. So our anti-clockwise moment is what? This is our anti-clockwise moment. 20 times 30 has to equal 50 times x. Therefore, if we cancel out, or rather, let's just make x subject to formula. Divide both sides by 50. You get this. And then we are left with 60 over 5. So we have what? 12 cm. Therefore, the weight 50 Newton must be kept at a distance 12 cm from the fulcrum. Do you understand that concept? Now, again, we might be given another case where we have multiple weights on one side. So let's say we have a beam balance, not a beam balance, sorry, a meter row. And on the meter row, we have a mass of, it could be either mass or weight. Let's just say 20 gram at the 10 cm mark. We also have another mass. This one is 50 gram at the 15 or rather 30 cm mark. This is the turning point at the 50 cm mark. And then we have ten or 100 gram at the 80 cm mark. Determine the weight of the mass x, or determine the mass x. So how do we go about this? The sum of anti-clockwise moments has to equal what? The sum of clockwise moments. This symbol means summation. So the sum of the clockwise moments has to equal sum of clockwise moments. How do we go about that? Let's take the moment for this 20 gram weight. This 20 gram, if this is 10 cm and this is 50 cm, then the distance between the 20 gram and the fulcrum is what? Is 40, because 50 minus 10 is 40. So the moment for the 20 gram is 20 times 40. So we add that to the other one, 50 at 30 cm mark. The distance between that and the fulcrum is going to be 20 cm. So we add that, 50 times 20 is equals to we take the clockwise moments now. So 100, if these are 80 mark, the distance between 80 and the 50 mark is 30. So we have 100 times 30. We add it to x times what is going to be the distance. Let's say it was kept at the extreme edge. So the distance from the edge, which is the 100 cm mark, to the fulcrum is going to be 50, right? So times 50. Now all we have to do is just simplify. 20 times 40 is 2 times 4 is 8, so that is 800. 5 times 2 is 10, so we have 1000 is equals to 100 times 30 is 3000, and then 50 times x is what? 50x. So we're going to have 1800. Bring this to over to the other side, becomes minus 300 is equals to 50x. Therefore x is equals to 1800 minus 300 is 15 all over what? 50, and this is going to give us 330, so 30 gram. So the mass of x is what? 30 gram for this meter rule to balance horizontally. Now another way we can alter the distance in balancing a meter rule is by moving the position of the fulcrum. This triangular thing here is called the knife edge. So another way we can alter the distance between masses is by moving the fulcrum. So usually we balance a meter rule at its center of gravity, which is at the 50 cm mark. So we usually balance it at its 50 cm mark. But if need be, and we place a mass here that is tending to pull this side downwards, we can alter the distance of the fulcrum in order to balance the weight of this body. So we move the fulcrum closer to the weight in order to neutralize its effect. So one thing you need to note that the weight of the meter rule always acts downward at its balance point, at its 50 cm mark. So now we're going to have the mass of the meter rule here. By doing this, you counteract the effects of the clockwise moment produced by this weight, and then it balances horizontally. We can then calculate the distance at which we are going to move the fulcrum to.